Okay, so the whole point of these questions is to use the first part of the fundamental theorem of calculus, which says that if we differentiate the integral, we essentially just get back the function inside. There's a couple extra things going on here for each of these problems. So for this first one, we notice that the x is in the lower limit of integration instead of the upper limit of integration. That means our answer is going to be the negative of what it would have been. So here, our derivative f prime of x is going to equal negative cosine of x plus 5x to the fourth. I guess I could use parentheses there or whatever. I like brackets. That's it. That's the whole answer. We're done. The point having been that we could have anti-differentiated and plugged in 2 and plugged in x and then differentiated and gotten back what we started with. But we didn't do any of that because we didn't need to do any of that. I will show that step in a minute. Similarly here, we're trying to find the derivative of the integral from 2 to x cubed of cotangent of t. So here, dy dx is going to equal cotangent of x cubed multiplied by the derivative of x cubed. Finally, this last one is extra weird. Well, extra weird from my perspective. There is, I know I was looking through the Babson homework assignments and there definitely was a problem like that. So I was like, oh, that's a good problem. We should do that one. So here we have x squared times a function of x that we're taking the derivative of. So we have to use the product rule. So our derivative here is going to be the derivative of x squared, which is 2x, times the integral from 1 to x of e to the 3t dt, plus, now we leave x squared alone. We multiply by the derivative of the integral, and the derivative of the integral of from 1 to x of e to the 3t is e to the 3x. It's kind of weird, right? If it were me, I'd probably take it a step further and actually do this integral here and plug in x and plug in 1, but it's not really what the point of this question was. So we'll just leave it like that. Yeah, kind of funky. So this is how you're intended to do problems like this, right? You're not meant to show any more work. I will show some more work now just so you can kind of get a bigger picture of what's going on here. But I really, really, really want you to take to heart that this is what's meant to be done when you're asked to find the derivative integral. You're supposed to be like, yeah, it's the function inside. Maybe I have to multiply by a derivative of the thing I'm plugging in. Maybe I get a minus sign if my variable's in the lower limit, but that's kind of the whole picture. Let's look at each of these a little bit more in depth. So for this first one here, I'll point out that if our function, I should have called it capital F, but I didn't. Oh well. If this is equal to the integral from x to 2 of cosine of t plus 5t to the fourth dt, then we can use the second part of the fundamental theorem of calculus, which is the evaluation theorem, which just says we can anti-differentiate each of those functions and then plug in the limits of integration and subtract. So we're going to end up getting, let's see, the antiderivative of cosine of t is sine of t. The antiderivative of 5t to the fourth is t to the fifth, evaluated between x and 2. Then we plug in, we get sine of 2 plus 2 to the fifth minus sine of x plus x to the fifth. I'll point out, you could have written plus c for each of these. And if you had, the plus c's would cancel, which is why when we find definite integrals, we don't ever write the plus c because not that you can't, you just don't need to. It always ends up canceling out with the other c that you would subtract. Here, that's my integral. And if I want to find the derivative, well, let's see. The derivative of sine of 2 is 0. The derivative of 32 is 0. The derivative of negative sine is negative cosine. And the derivative of negative x to the fifth is minus 5x to the fourth, which is exactly the same as the answer we got up there. Again, we don't want to do it this way. And a lot of times we cannot do it this way. But it's nice to see that, oh yeah, it works if we do it this longer way. You're welcome to ask questions, but I'll keep going. Let's look at this next one, but I will stop if you have questions. Ooh, this next one's a little interesting. Cotangent. So what's the antiderivative of cotangent? Well, you're going to learn this eventually anyway, so we might as well. So to do the integral from 2 to x cubed of cotangent of t dt, I'll point out that cotangent is the same as cosine of t divided by sine of t. And I'm not going to say it just quite yet, but I'll just point out that, well, I'll tell you what the answer is. Well, I'll give you a hint anyway. What's the derivative of the natural log of sine of t? Well, let's see. The derivative of the natural log of some stuff is 1 over the stuff multiplied by the derivative of the stuff, which is positive cosine of t. Oh, look, that's exactly cotangent. So we do need one more thing, that we need an absolute value. So when you anti-differentiate cosine of t over sine of t, you end up getting the natural log of the absolute value of sine of t, apologies, evaluated from 2 to x cubed. Yes, we're going to write the absolute value, but we really just kind of ignore it the whole time. So that's going to be the natural log of the absolute value of sine of x cubed minus the natural log of the absolute value of sine of 2. And then if we take the derivative of that, I called this y before. So now if I want to find the derivative, dy dx, it's going to equal, let's see, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff, and the derivative of sine of some stuff is cosine of that stuff multiplied by the derivative of the inside stuff. And oh, look, that's cosine over sine, which is cotangent of x cubed multiplied by 3x squared, just like we got up there. So cool, it works. Yes. So I knew what there's a way to find the antiderivative of cotangent, which we might actually get to at the end of class today, but I was just giving it to you there. So yes, there is a process for that, which we will get into. Yeah, I guess today. Other questions? Okay. So raise your hand if you're in Babson's class. So you all have seen him talk about, wow, almost everybody. Raise your hand if in Parlax's class. Okay, wow, singled out. Well, fortunately, I guess I know that means which way we're probably going to end up going for the most part. It won't be terrible, but it will be challenging. Challenging is not the right word. It's unfortunate that we're going to go yeah, I don't know. We'll see what we can do here. So most of you have seen him talk about the fundamental theorem of calculus. He did it a little bit differently than I talked about it. I do think it's worth talking about because there was something in the way he did it, which I think could just bears a little bit more explanation. So I'm going to revisit the first part of the fundamental theorem of calculus for just a couple minutes here. And I have to remember how to do it. Oh, yeah. Okay, so here's the idea. Here's another way of showing. So what are we trying to show? We want to show that this really and truly is an antiderivative of f of x. That's kind of the whole goal. But there's another way of saying that, right? Instead of saying it that way, what we're really going to say is we're going to show that if we call this thing capital F of x, the way you show something is an antiderivative of something else is we want to show that the derivative of capital F is equal to little f. That means everything we want it to mean. This means that capital F of x is an antiderivative of little f of x. And there's really not a better way of writing it. Well, let's write it like this. Okay, so let's give us some meaning here. Let's say that Be very, very intentional with how I draw this. Okay, so this area here under f of t, I don't know why I wrote dt there. I'm sorry, that's crazy. There should be no dt there. Pretend like you never saw it. This area is, we're going to say that area is f of x. So we'll use some nice colors here. We'll use red really lightly here. So we're going to say that f of x is indeed equal to the area under the curve from a to x under the curve f of t dt. And then we're also going to, well, we're going to find the derivative of f of x, of capital F of x, sorry. So, and we're going to go all the way back to 21a and say that the derivative of capital F of x is equal to the limit as h approaches 0 of capital F of x plus h minus capital F of x all divided by h. So let's see what capital F of x plus h is. So going a little bit to the right of x, say like here's x plus h. So this area in blue, which includes the area in red, that's my capital F of x plus h. It's the integral from a to x plus h of f of t dt. All right. So here's the thing we have to kind of focus on for a second. That as we let h go to 0, this point over here is going to move towards that point over there. Okay, hold on to that while we're going to do a little bit more here. So I'm going to rewrite this as the limit as h goes to 0 of, well, the blue area minus the red area is just this leftover, I have purple, this leftover purple area. That's your f of x plus h minus f of x. Or as I'm going to write it in just a second here, it's the integral from x to x plus h of f of t dt. Okay. Yeah, we're going to do some side work over here. Here's what I want to show you. So that purple area. I can use purple. So the purple area, aka the integral from x to x plus h of f of t dt. You could definitely say that it's less than or equal to the area of the rectangle whose base is h and whose height is whatever the maximum value of the function is on that tiny little interval. So it's less than the height times the maximum of, notation, sure, the maximum of f of x, where x is between, I should say f of t, sorry. T is between x and x plus h. And similarly, that area is bigger than or equal to the base of a rectangle times the minimum value of the function f of t, where t is still between, sorry, I wrote that really terribly. I apologize. That's awful. Crimes. So this purple area is between the area of two rectangles. But now look what's going to happen. As x plus h goes to x, or as h goes to 0, the maximum value of the function on the interval and the minimum value of the function on the interval both just get closer and closer and closer to f of x. Right? If we scooch like way over here, right, the maximum value and the minimum value are both essentially f of x. So here's what's happening. As h goes to 0, we have that this amount here becomes h times f of x is less than or equal to the limit as h goes to 0 of the integral from x to x plus h of f of t dt is less than or equal to h times of x. And then if we divide everything by h, check it out. that limit is less than or equal to f of x and bigger than or equal to f of x, so it has to be f of x. But that means that this limit up here is f of x, exactly like we wanted it to be. It feels a little hand wavy, but not a lot. Like you could definitely walk through these steps and be like, okay, well, that seems plausible. The whole thing is not unreasonable. That essentially you're saying the derivative of this change in area is essentially just the height of the function. Or let me I said that how I want to say it. Yeah. The derivative of the change area is essentially the height of the function. Thoughts, questions, comments? Like why? Well, because we need it. So, not that you should ever need to reproduce the fundamental theorem of calculus proof, but it's good to have seen it so you can at least be like, well, I kind of believe that, yeah, the derivative of the integral gets you back the function you started with. The integral and the derivative should undo each other. So I know I've said it a lot because I think it's super important, but I'm going to say it again. The derivative and the integral undo each other. So that's kind of the whole story with this fundamental theorem of calculus. And much like how in 21A, after we talked about the limit definition of the derivative, then we kind of just left it in the dust and started doing all sorts of other things with differentiation. The same is going to be true about integration, right? We have said the fundamental theorem of calculus part 1. We're going to talk about how that means we can integrate things, and then we're going to start talking about different methods of integrating things. And since almost everyone is in Babson's class, at least currently, that's the direction he's going first, is he's going from chapter 5 to chapter 8 to talk about methods of integration, and then going back to chapter 6 to talk about the applications like finding volumes and lengths and surface areas and other weird physics things. So that's where we're going. Let me see. Yes. So what this, and so then just to reiterate, I know I said it last time, I'm saying it again. So the fundamental theorem of calculus part 1 just says that the derivative of the integral from some constant to x of f of t dt is equal to f of x. I would also point out there's a more generalized version which says that the derivative of the integral from a to some function of x of f of t dt is equal to that function of g of x multiplied by g prime of x. But really, it's just the chain rule again, just like the chain rule always shows up when you learn new derivatives. And then the second part, which is the part you are actually going to use more of the time, is that the integral from a to b of some function of x dx is equal to the any antiderivative of little f evaluated between a and b, or capital F of b minus f of a, where of course capital F of x is any antiderivative of little f. And that's the way we write that, right? That thing I just wrote there means capital F is an antiderivative of little f. It also means the derivative of capital F is equal to little f, but that's really what we're trying to say when we write that. Okay, so what that means for us now is that we can find all sorts of definite intervals. For example, we can evaluate the integral from 0 to pi of sine of x. And it's relatively not terrible. We find an antiderivative. So let's actually, I'll do this in a somewhat strange way. What's an antiderivative of sine of x? Negative cosine. So let's say negative cosine of x plus 3. Right, that's an antiderivative. It's valid. It's not what we would normally write, but it's totally fine. Evaluated from 0 to pi. So then we always plug in the top limit first, and we get negative cosine of pi plus 3 minus, then we plug in the bottom limit second, negative cosine of 0 plus 3. Let's see what we get here. We get Negative cosine of pi is -1 plus 3. Minus a minus is plus. Plus cosine of 0 is +1. And then minus a +3 is -3. And hey, look, those 3's definitely cancel. And it wouldn't have mattered if they were 3's or 30's or a billion. They would still cancel no matter what they were. So we don't ever need to write that plus a constant, whether it's 3 or c or anything. You can, it's not necessary. -1 plus 1 is 2. So that means that not just the area under the curve, but the net area that is above the x-axis and under the curve is 2. Here it just looks like that, right? That's what that function looks like, that part of the function. Yes, exactly. And so I'll say something that I say often is that definite integrals, all that means is what? Your integral has limits of integration. Definite integrals equal a number. Some finite number. It could be 2, it could be pi, it could be the natural log of 7, but it's going to be some numerical value that does not have any variables in it. On the other hand, indefinite integrals end up being functions. Or in other words, indefinite integrals are just the antiderivative, and you're not plugging anything in. So if it was, right, the answer without this would be just negative cosine of x plus c, because we want the general antiderivative, not just some specific one, unless you have an initial condition and then you have to solve for the c value. Yeah. Let's look at another example. Actually, let's say something. I feel like yeah, everything's all over the place. That's fine. That's not the page I was looking for. Sorry. So, sorry. What if I want to find the integral from 0 to pi over 3 of secant of x plus tangent of x, quantity squared? Ugh. So when in doubt, multiply things out. We multiply out secant plus tangent times secant plus tangent. That's going to be the secant squared of x plus secant times tangent plus another secant times tangent. So 2 times secant x times tangent x plus tangent squared x. And I would say that 2 of those pieces, you already know the antiderivative of. What's the antiderivative of secant x times tangent x? Secant x. What's the antiderivative of secant squared x? Just tangent, right? Because the derivative of tangent is secant squared, and the derivative of secant is secant x tangent x. What about the tangent squared? Well, it's not as hard as you think it is once you know the trick. And the trick is use a trig identity. My favorite trig identity, which if you're new to this class, prepare to hear something you can never forget. 1 plus tangent squared x equals secant squared x, or as a student of mine once said, I tan and get sexy. Unforgettable. I tan and get sexy. 1 plus tangent squared x equals secant squared x, right? You will never, I've tried to forget it, it's impossible. So what that means though, is we can say that tangent squared x is equal to secant squared x minus 1. And then we know what the antiderivative of secant squared is, and we know what the antiderivative of 1 is. So we're going to rewrite this as the integral from 0 to pi over 3 of secant squared x plus another secant squared x is really 2 times secant squared x plus 2 times secant x tangent x minus 1. Could you break this up into 3 integrals and pull out some 2's? Sure. Do you need to? Absolutely not. You can say this is going to be, well, the integral of secant squared is tangent. So you get 2 times tangent of x. The antiderivative of secant x tangent x is going to be secant x. So you get 2 times secant of x. And the antiderivative of -1 is negative x, evaluated between 0 and pi over 3. The bad news is you have to know what tangent and secant of pi over 3 are. So, okay, so we're going to get 2 times tangent of pi over 3 plus 2 times secant of pi over 3 minus pi over 3 minus 2 times tangent of 0 plus 2 times secant of 0 minus 0. Simplifying, tangent of pi over 3 is equal to root 3. Secant of pi over 3 is equal to 1. Sorry, cosine of pi over 3 is 1/2, so secant of pi over 3 is 2. And tangent of 0 is 0. Secant of 0 is 1. And we get the 0 there as well. So we end up with, let's see, 2 root 3 plus 4 minus 2 is plus 2 minus pi over 3. Kind of a funky answer, but it is an answer. Double check, make sure I didn't do anything stupid. Yeah, that's right. No, okay, yeah. Mistake. All right, cool. Yeah, looking good. So, no, I'll say it again. This integral just represents how much area is under this curve between 0 and pi over 3. And it's correct to say under here because I know this curve is always above the x-axis because it's something squared, so it's always not negative. That said, though, so keeping things in order here. Note. When we find the integral from a to b of f of x dx, we are computing the net area under f of x that is above the x-axis. So for example, if I said I want to find the integral from 0 to 4 of, what am I looking for here? X times 2 minus x. Yeah, that seems good. I'll point out that function is not always positive, right? If we graph this thing, it's a parabola. It's opening downward. It's got x-intercepts at 0 and 2. And the vertex is 1, 1. And then at 3, I would get 3 times -1, which is -3. I don't know why I started using red. It looks something like this. Should have gone to 3. Oh well. And then 4 is 4 times -2 is -8. Ugh, okay, fine. So what we're looking at is this area getting counted as positive, and this area, use a different color here, getting counted as negative. And so we'll do whatever this is minus however much that is, and that'll be what this integral ends up representing. So if I just want to calculate the definite integral, I don't have to actually think about this at all, right? It's nice to know that that's what we're doing, but to calculate it, just proceed as usual. Multiply this out. You get 2x minus x squared dx. Anti-differentiate. You get x squared minus x cubed divided by 3. Evaluated from 0 to 4. Bless you. Plug in 4. You get 4 squared minus 4 cubed over 3. Think about plugging in 0. Observe that in this case, you will get all zeros and write down nothing. Or write down -0. But just be careful, right? Because you don't always get 0 when you plug in 0. Notable exceptions, cosine of 0 is 1, secant of 0 is 1, e to the 0 is 1. So make sure that if you're thinking about plugging in 0 and getting all zeros, you're really getting all zeros. That's going to be something. What, I don't know. 64 over 4 minus 64 over 3. Why did I do that? Oh, so I could factor out 64. So that's 64 times 1/4 minus 1/3, which is 64 times 4 over 12 minus 3 over 12 is 1 over 12. So I get 64 over 12 or 16 over 3. Interesting. I don't know, that was a weird way. That's a weird way of doing that. Sorry, that's just what my brain saw right off the bat, and it just went there. I often like to try to make the numerator factor, but a probably more typical way of doing this would have been to multiply the 16 by 3 over 3 like a normal human being and subtract 64 over 3 and get a different answer. Oh yeah, that should have been that. So good thing I checked. Also, if you guys said you guys could have said something if you noticed, I made a mistake here. 1/4 minus 1/3 is negative 1/12. So I'm getting negative 16/3. I was going kind of fast though, so no worries that you didn't say anything yet. So I do get, yes, negative 16/3. So the net area is negative overall. So what if instead they'd asked us to find the total area between the curve and the x-axis? Well, then you have a different process to go through. If we want to find the total area between f of x equal to 2x minus x squared and the y-axis, or g of x equal to 0, on the interval from 0 to 4, we have to break it up into the positive parts and the negative parts. Luckily, we've already graphed it. We can see that we go from positive to negative at 2. So here's what we would do. We would say it's going to be the absolute value of the integral from 0 to 2 of 2x minus x squared plus the absolute value of the integral from 2 to 4 of 2x minus x squared. Which is kind of a pain, but it works. So then we would get the same sort of results. We'd have x squared minus x cubed over 3 evaluated from 0 to 2, absolute value of all that, plus the same thing over here, x squared minus x cubed over 3 from 2 to 4, absolute value of all that. Simplifying here, we get 4 minus 8/3 minus 0 plus plug in 4, you get 16 minus 64/3 minus plug in 2, you get 4 minus 8/3. And then we go to work. Let's see. 4 minus 8/3 is 12/3 minus 8/3, which is going to be 4/3. Plus over here, let's see. All right. Absolute value. 16 minus 4 is 12. Negative 64 plus 8 is negative 56. That seems terrible. Let's see. 12 is 36 over 3 minus 56 over 3. So that's going to be 4/3 plus 36 minus 56 is negative 20. So the absolute value of negative 20/3. Finally, we get 4/3 plus 20/3, which is 24/3, which is the best number ever, 8. I was born on 8/8. That's why it's my favorite number. So, okay. Interesting. Right? So the total area is 8, whereas the net area is the difference of those two things, which was negative something.
Could you explain again, why did you split up into integrals?
Right. So the reason I did that is because I want to count both areas as being positive so that I can calculate the total area. So what I'm doing is I'm calculating both. Sorry. This part here, that part there is my 4/3. And this part here, which was getting calculated as negative before, but now we're calculating as positive, is going to have an area of 20/3. If we subtract those, what do we get? What's 4/3 minus 20/3? Oh, negative 16/3. What a surprise. So it works, right? If you're calculating just the definite integral without kind of thinking about anything, it's what we usually do. You just get the net area that is above the x-axis. In this example, since there was more area below than above, we ended up getting an overall negative amount of area. But if you wanted to actually tabulate all of the area, we don't care whether it's above or below. We just want to know how much area there is. Then we have to kind of count anything above as positive, and anything below that would have gotten counted as negative, we have to make it positive by taking the absolute value of it. There is a different way to kind of account for that, which we will get to in a little bit. Unfortunate. Oh well. So. So yes, definite integrals are fun. Oh yeah, we should talk about that too. So the other thing, there are a few other integral properties we didn't talk about. One I can think of that I think is moderately important is this one. So some integral properties. Bless you. If you sneeze and I don't say bless you, just know that I thought it in my head and just saying something else. Or consent height or any appropriate acknowledgement of your sneezing. So some integral properties. One that I think is really worthwhile is that the integral from a to b of any constant is just the area of a rectangle, right? What you've really got here is some rectangle with a height of c and a base of b minus a. And that area is the base times the height. Not too terrible. I feel like I've said it, but I'll say it again. If you have the integral of a constant times your function, it is always fine to pull that constant out in front of the integral. We do it all the time. What else? There's a few other ones here that are important. We said this last time, the integral from a to a of any function is going to be 0 because you don't have any base. It's all just height with no width. We also said the integral from a to b of f of x is equal to the negative of the integral from b to a of f of x. If you change the order of the limits of integration, it changes the sign of your integral. There's one other thing, at least. Oh yeah, we'll save that one for the next page. Sorry, I'm trying to remember. There was one. Where is that piece of paper? There it is, tiny. Oh yeah. Two more things. We use this one all the time, but we actually never really use it. I know that sounds silly, but you'll know what I mean in a second. So the integral of f of x plus g of x, we did one like that already, right? We had a couple things added together, we just integrated everything. But the thing we're kind of doing and not doing is you can break it up into two integrals and integrate each thing and then add the results together. And just kind of like with derivatives, how we would take a derivative of a bunch of things added or subtracted together and just take all the derivatives and add or subtract the results together. The same thing is true for integrals. In fact, a lot of the sum and difference and constant multiple rules that are true for derivatives are also true for integrals, which is nice. And it's true if you're adding or if you're subtracting. And then the last one, which I think deserves its own page because it needs a picture. The last one that's on my mind right now, I should say, is the following. Let me draw the picture first. I'm actually going to draw a second picture as well. But here's my first picture. So what I want to do is I'm going to pick some number C here. And so all I really want to point out here is that these two areas from A to C and from C to B is all the area from A to B. So writing that this way, we can say that the integral from A to B of f of x dx is equal to the integral from A to C of x dx plus the integral from C to B of f of x dx. And while that might not seem super exciting, it's very useful. What I think is, I don't know if it's exciting, but certainly interesting is C doesn't have to be between A and B. Let's see what I mean. I'm really just going to draw the same picture and put like A and then B and then C. Okay, so I'm saying this is still true. Well, let's start out by writing a more normal statement. I'm going to write the integral from A to B plus the integral from B to C is equal to the integral from A to C. Everyone good so far? All right, it's the same thing, just written with the different letters. Okay, but now check it out. I want to get this side by itself. So I'm going to bring that over there. So I'm going to write this as the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx minus the integral from b to c of f of x dx. But then I can interchange the limits of integration and change the sign and get that the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx minus a minus or plus the integral from c to b of f of x dx. Kind of cool. So you can break up an integral at any point. It does not have to be between the limits of integration. It usually makes sense to do it between them, but it does not have to be between there if there's another convenient value for whatever reason. Kind of interesting. Okay, and then the last sort of thing that is in this section in my mind is the average value, which is really not hard at all if you know how integrals work, which you all do at this point, at least enough. Average value, also known as average height of a function, is literally just that. If you got some function, let me ask, I'm going to date myself here. Do any of you know what an ant farm is? See some nods. Okay, so yes. So an ant farm is like, you get this like little rectangle thing and put like this little weird white sand in it, and then you put ants in it and they would like crawl around and make tunnels and stuff. And the sand would maybe look something like in your little rectangular prison for the ants, you would have some sort of like that, right? And not that I would do this, but if you were then to shake it all up and level out the sand, the amount of sand hasn't changed. But now that sand is all at the same height, which would be the average value of whatever we're pretending that function is. So if you shake it all up, same thing, but now there's some like average value. So this area here and this area here are the same. And this height, where it's all level, is the average value of the function, which we're pretending like the ants made some cool sine function or something. Or in other words, to find the average value, you take the area divided by the length to get the height. So in general, the average value of f of x is equal to 1 divided by b minus a times the integral from a to b of f of x dx. Or as I just said, the area under the curve divided by the length of the interval we're integrating over. I have an example. So to have an actual concrete example, find the average value of, sure, f of x equal to 3x squared plus 2x plus 1 on the interval from 1 to 3. All you're really doing is finding the definite integral like you usually would and then dividing by a number. So our average value here is going to equal 1 divided by 3 minus 1, or 1/2, times the integral from 1 to 3 of 3x squared plus 2x plus 1 dx. So that's going to be equaling 1/2 times, our antiderivative is x cubed plus x squared plus x from 1 to 3. That's going to be 1/2 times, plug in 3 first, you get 3 cubed plus 3 squared plus 3, minus plug in 1, you get 1 cubed plus 1 squared plus 1. That's going to be equaling 1/2 times, let's see, 27 plus 9. Plus 3 minus 3 cancels out. The 3 is there, that's why I didn't write them. And then 1/2 of 36 is 18. I'm not great at drawing this, but let me show you because I do think it's kind of neat to show. Yeah, we can probably make this look decent. Let's try. So if I were to graph this, oh, check this out. This is kind of cool. So the function is y equal to x cubed plus 3x, sorry, plus, what is the function? Not x cubed. It's 3x squared plus 2x plus 1. Sorry. 3x squared plus 2x plus 1. I don't know if you know this or not, but there's an easy way to like get the area under a curve. You just say you want y to be less than or equal to that. Oh, that's too much. I don't want all of that. I want still above the x-axis, so I want to be greater than or equal to 0. And I don't want everything from negative infinity to infinity, so I need to change my limit of integration to be from 1 to 3. Cool. And let's zoom out just a little bit. Oh my gosh, it's so tall. Okay, that's kind of, so okay, it doesn't look great, but there's your total area. Whereas the average value is going to be just y equal to 18 on the same interval. I forgot to do the less than part though. Not 18. Oh my goodness. So that blue area there should be the same as all the red area that we're seeing. It's the average value. It's the average height. This little missing part here is exactly how much area we have up there. Kind of cool. So average value, really easy to calculate. You just do the integral, divide by the length of the interval by subtracting the top value minus the bottom value. All right. In Babson's class, did you all start talking about finding the area between two curves? Okay, good. All right. Not good, but I mean, good to know that that's where I'm going next. So yeah, I guess then we should probably start talking about u-Substitution. Come back to you here later. Yeah, sorry, one second. Got papers all over the place. So I will mention before we get going here, we've already talked about u-Substitution a little bit. We were doing some, what I like to call mini u-Substitutions, kind of at the very beginning, we were talking about antiderivatives. Yeah, let's see here. Cool. All right, examples. So, u-Substitution. Substitution. I can spell, sure. Or as I would encourage all of you to think about it, undoing the chain rule. That's actually what's going on here, is we're trying to undo the chain rule. We're trying to find the derivative that you would have taken, but there's also a chain rule that's happening when you took that derivative. So let's look at a very straightforward example. Let's say we want to find the antiderivative, the indefinite integral of 2x times x squared plus 6. This one's easy enough that you could just do it straight away the normal way, right? You could multiply it out and say, okay, I'm going to have the integral of 2x times x squared is 2x cubed. 2x times 6 is 12x. And then just anti-differentiate and get 2x to the fourth divided by 4 plus 12x squared divided by 2 plus a constant. And simplifying, that would be 1/2 x to the fourth plus 6x squared plus a constant. That'd be totally fine. But a lot of the times it's not going to be that easy to multiply out or impossible to multiply out. You might have something like 2x times x squared plus 6 to the 1,000th power, or 2x times the square root of x squared plus 6, which you can't multiply it out. So the idea here is to kind of think about what part of this integral, if you took its derivative, would look like another part. So what can we pick so that if we took its derivative, we would also have that. Exactly. The x squared plus 6. Usually, it's something that's inside the parentheses, inside the square root, inside the trig function, inside an exponent, inside the denominator, something that is stuck inside some other function. Usually. So we're going to let or choose u to be equal to the thing whose derivative is also showing up. And then we're going to take the derivative. So our derivative of u with respect to x is going to equal 2x. People like to do this in lots of different ways. I would say there's probably 3 ways of doing this that all feel the same-ish, but are all slightly different. Let me show you the way I prefer, and then I'll show you the other 2 ways as well. So I prefer to do this. I prefer to say, oh, look, my integral has a 2x multiplied by dx. So I'm going to make this equation look like that. So I'm going to multiply both sides by dx and say, great, I have du equal to 2x times dx. And then I'm going to start replacing things in my integral. Now, in my integral, I would say that u-substitution, I would also subtitle it as a translation experience or problem. We are translating from the language of the variable x to the language of the variable u. And we can't have some of each. We can only have x's or we can only have u's. And that is especially important when we are talking about the dx and the du. You cannot have something with u's and a dx. You cannot have something with x's and a du. The differential, that's what that d thing is called, dx, du, whatever. The differential variable has to match the variable that we're integrating. So what that means for me is I am always focused on making sure that my dx thing here transforms into a du thing in my new integral. So when I write this down over here, my integral, and I'm going to actually rewrite this as x squared plus 6 times 2x times dx. I'm going to first focus on making sure that, oh yeah, I'm going to replace the 2x dx with du. And then I'm going to focus on the rest. And that's really important because sometimes if you focus on the rest first, you actually lose the piece you need to go with the dx to turn into du. So really, 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 I will say it 1,000 times. You want to make sure that dx paired with whatever has to go with it turns into du, and then look at the rest of the things. So then we're going to say that this is our u. We're going to rewrite this as the integral of u times du, or u to the first times du. And then that's going to equal u squared divided by 2 plus c. And then, since it's an indefinite integral and the answer has to be a function, the function has to be using the same variable we started with, so we have to turn it back into a function of x. So we are going to replace u with what we said u is equal to, which is x squared plus 6. So we're going to rewrite this as x squared plus 6 quantity squared divided by 2 plus c. Question: are these answers the same? Let's find out. Let's multiply this out. You multiply this out, you're going to get x squared squared plus 6x squared plus 6x squared, which is 12x squared plus 36 divided by 2 plus c. And then if you divide each thing by 2, you get x to the 4th over 2, or 1/2 x to the 4th. You get 12x squared over 2, which is 6x squared. You get 36 over 2, which is 18, plus c. Are those the same? Well, it depends on your perspective. They're the same enough. Or if you are a little bit more careful, these constants aren't necessarily the same. So that constant there is really that constant plus 18. So as long as they only differ by a constant, right? We've talked about how antiderivatives, you always throw on a plus c. That constant can be anything. So here our constant is c1. Here our constant is 18 plus c2, because 18 is a constant. So as long as doing it a different way only gives you a different constant added at the end, you're totally safe and fine. All right. So I did mention I would talk about how there's a couple other ways of doing this. Let's see here. Let me think for 1 second. You do it that way or that way. That way is kind of weird though. So yeah.
Is du also like a variable you're working on?
Du is what here's what I would think of as du. Du is the derivative of u multiplied by dx. So du is always just the derivative of u multiplied by dx. Whatever that derivative happens to be. In this particular example, my du is exactly 2x multiplied by dx.
So when you did the integral for you used like the rule of n plus one over n plus one.
Right, because
And then
I'm
what happens
integrating
with
the variable u with respect to the variable u. So this d thing here, that tells you what variable you are anti-differentiating. That's why the variable here has to match the variable there. They cannot be different. Or, well, we'll talk about that when we get to 21C. 21C or 21D, actually, I think. Okay. Which we don't have a code class for, so you can come see me in person. All right, so let's look at another example, and in the next example, we'll talk about how you can do this in a few different ways. So let's look at something a little more complicated, something we couldn't just multiply out on its own, like, I don't love that one. Sure, let's do the following. Let's say we wanted to find the indefinite integral of x squared times 4 plus x cubed to the 21st power. Based on what I've said already, what's a plausible choice for you? Right, it's the thing that's stuck inside some parentheses. Now, I'll point out that if we choose this for you, which is the right choice, our du isn't going to perfectly show up. Our derivative isn't exactly there. That's okay. The derivative here, du dx, is equal to 3x squared. As long as you're only off by a constant multiple, it's not an issue. We have an x squared, we're good to go. So there's 3 different ways of doing this, and I will show you all of them right now. So one way of doing this is the way we did it before. My preferred way, the James way, the best way, is to say that du is equal to 3x squared dx, and then I'm going to make the right-hand side look like what I already have in my integral. Since I already have an x squared times dx, I'm going to multiply both sides of this equation by 1/3. So I'm going to say that 1/3 times du is equal to x squared times dx. And then I'm going to rewrite this integral. You don't need to rewrite the order here. I'm just doing it to make it super obvious what's happening. I'm going to rewrite it as 4 plus x cubed to the 21st times x squared dx. And then I get to replace the x squared dx with 1/3 times du. And the 4 plus x cubed will be u. This will end up equaling the integral of u to the 21st times 1/3 du. And we would almost always just put the 1/3 out in front of the integral from the get-go. We're going to stop there. We'll come back to it. Another way of doing this, which I don't love personally, but lots of people like, is taking this du dx equals 3x squared and actually still doing the same multiplication and saying that du is equal to 3x squared dx, and then dividing both sides by 3x squared. So in other words, some people really like to isolate the dx. This works great if your u-substitution is going to work out perfectly, like a lot of our examples will foresee. But later on, we're going to have some u-subs where things are more complicated and it doesn't always work out so nicely. But here it's totally fine. If I rewrite my integral as, so I'm just going to take my integral here, my integral of x squared times 4 plus x cubed to the 21st power times dx. I'm just going to replace the dx with du over 3x squared. Yes, I'm going to have some u's and x's at the same time. That's okay. So we're going to have the integral of x squared times 4 plus x cubed to the 21st times du divided by 3x squared. What can I cancel? The x squared. So then this 4 plus x cubed is going to be my u. And look, I've got the same thing. I've got the integral of u to the 21st times du divided by 3, or 1/3 times du. The last one I'm going to show you, some people like, most people don't. What some people like to do is instead of making the thing over here look like what I have, so instead of making my 3x squared dx look like x squared times dx, I'm going to make my integral look like that. So I'm gonna take my integral of, I'm gonna rewrite it as 4 plus x cubed to the 21st times x squared dx. I'm gonna rewrite it as 1/3 times the integral of 4 plus x cubed to the 21st times 3x squared dx. I find this annoying, but it works. 3x squared dx is exactly my original du. That is my u. So again, I'm going to get 1/3 times the integral of u to the 21st times du. And hopefully you all see that no matter which way you approach it here, you're still getting to the same place. You're still getting to 1/3 times the integral of u to the 21st power. You can do it whichever way you want. I personally tend to prefer this first way, where I like to make my du dx equation look like exactly what I have inside the integral and then adjust accordingly.
For the third method, where did the 1/3 come from?
Well, so I told myself I wanted to have a 3x squared, but I can't just multiply by 3. I can only multiply by 1. So I multiply by 3 and by 1/3 to end up being equal to 1. So right, this 3 here and that 1/3 there are technically canceling each other out. I'm not going to cancel them out, but they would cancel out. So this integral is the same as that integral, right? I've just multiplied by 1/3 and by 3. But then, 3x squared dx is my du. 4 plus x cubed to the 21st is my u to the 21st. In either of these three cases, in either of these three cases, the integral of 1/3 times u to the 21st du is going to be 1/3 times u to the 22nd divided by 22 plus c. And then we're going to switch back to x's and get 4 plus x cubed to the 22nd divided by 66 plus c. And you can see that if you took the derivative here, you would exactly get 22 times 4 plus x cubed to the 21st times 3x squared. And the 22 times 3 is 66, which cancels the 66 that we're dividing by. So it totally works out. It undoes the chain rule. So when attempting an integral, you're going to eventually have lots of methods available to you. And the hard part about integration is you're not always going to know which method you should try first, or which method's going to work. Not every method is going to work for every integral. But I would say u-substitution is kind of your go-to first thing to try after you have maybe simplified the thing first. So first thing you should do is just look at it and be like, can I integrate it? If the answer is yes, great. If the answer is no, can you simplify it so you can integrate it? If the answer is yes, great. If the answer is no, then you start thinking about methods. And the first method you usually want to at least consider is there a viable u-substitution? Yeah.
What makes us know, like what makes something?
So what kind of things do we know how to integrate? Well, any function that you recognize as a derivative of something else. So you know how to integrate x to any power. You know how to integrate 1 over x, which is going to be the natural log of the absolute value of x. You know how to integrate e to the x, which is e to the x. You know how to integrate any trig derivative you know. So you can integrate cosine, sine, cosine, comma, sine, comma, secant squared, cosecant squared, secant x tangent x, cosecant x, cotangent x. Or any of the derivatives of the inverse trig functions, like 1 over 1 plus x squared, or 1 over the square root of 1 minus x squared, or 1 over x squared of x squared minus 1, which I definitely wrote down all of those in the previous class, and there's a whole list of all the things we know derivatives of. And there's also a couple lists on Canvas of functions you should know derivatives of and antiderivatives of. So anything you know how to differentiate and get an answer, you know the antiderivative of that answer is the original function you started with. But now, if it's not something like that, that's when we have to be like, well, what else can we do? So for example, what if someone hit us with something like the integral of tangent to the 5th x times secant squared of x? Wow, that's kind of crazy. We're going to try u-substitution. So again, and actually this is what I was trying to say before I forgot about it. So how do we pick u? there are two things you want to look for. I should say, actually, there's one way to help you decide, and there's one thing you want to be true. So look for things that are stuck. Meaning you have something like the square root of some stuff, or e to some stuff, or cosine of some stuff, or really any trig function of some stuff, or 1 over some stuff, or some stuff to a terrible power. Basically, anything that's an argument of another function is typically a good place to at least think about trying. So here, oh, and then the second thing is what we want is that whatever we choose, we really want the derivative of that to also be there. So we need the derivative of u to also be present in the integral. And that second part is more important. The first part just helps you kind of identify what kind of things might be a good choice. But the second part is we want to make a choice so that second part is true. So based on that second part, what might be a good relatively, and you want to also pick things that are basic. Like you wouldn't pick tangent to the fifth here when you could just pick tangent. Or you wouldn't pick secant squared if you just pick secant. You want to pick something that's relatively not terrible to find the derivative of in the first place. So based on the fact that we want the derivative of our thing to show up, what's a good choice for our u here? Tangent of x, because what's the derivative tangent of x? Oh, and we have a secant squared. How wonderful. So we're going to let u equal tangent of x. Our du, so we usually skip the step of writing du dx equals the derivative and just skip straight to saying du equals the derivative multiplied by dx. It's all, but it's important to remember that the way you find du is by literally taking the derivative of u. And then you just bring the dx over to the other side. Well, great. This is going to work out perfectly. We're going to have the integral of tangent to the, well, so I should say my secant squared x dx is going to be my du, right? All of this, all of that is replaced by du. And then my tangent to the fifth x, or tangent of x raised to the fifth power, is just going to be my u to the fifth power. And then we have to differentiate. We get u to the sixth divided by 6 plus c, which becomes tangent to the sixth power of x divided by 6 plus c. Cool. Now, later on, we'll talk about how we actually could have chosen u to be secant as well, and it would have worked out just fine. But there's some weird stuff with secants and tangents that we don't need to talk about just yet. How much time have I got? I got 10 minutes. All right. Yes. Okay, sure. So let's look at a couple more examples. Something like the integral of the natural log of x to the 8th power divided by x dx. Oh yeah. I've got lots of examples. Cool. So what's a good choice for you here? Yeah, because u equals the natural log of x, your derivative is 1 over x, and your du is 1 over x times dx. Sometimes I find it helpful to rewrite this as the natural log of x to the 8th times 1 over x times dx. Just to make it absolutely clear that, oh yeah, my 1 over x dx is my du. This is going to be the integral of my du times, I really can't stress enough, do that part first. And then what's left, just the natural log of x to the 8th, which is my u to the 8th. All of that is replaced by du. That's my u to the 8th. The rest is not terrible. U to the 9th divided by 9 plus c, which is going to be the natural log of x to the 9th divided by 9 plus c. Weird but important question. Do I need the natural log of the absolute value of x? No, because I didn't anti-differentiate 1 over x to get there. You only ever need the absolute value if you're actually doing the antiderivative of 1 over x to get the natural log of the absolute value of x. Like in this next question. The integral of, sure, cotangent of x. That looks terrible. So for trig functions, if you don't know what to do, take it back to sines and cosines. So cotangent of x is the same as cosine of x divided by sine of x. What should we choose for our u here? Why not cosine? Sure, but we can fix a negative. We'll come back to that. Let's try u equals sine. Our du is certainly the derivative of sine, which is cosine of x times dx. And that's great. I've exactly got it, cosine of x times dx. That's going to be equal to my du. And then the sine of x is u. So this integral is going to equal the integral of du divided by u, which unfortunately is how a lot of people like to write it. I personally would prefer to write this as 1 over u times du. So that then it's more obvious. Oh, we're integrating 1 over u. We get the natural log of the absolute value of u plus c. And then we change it back to the natural log of the absolute value of sine of x plus c. Okay, so let's do the integral of tangent as well. Maybe. Oh yeah, there's something else. There's something. Oh, there's something I've been. Yes, how much? Okay, we got time. Yeah, sure. Barely though, but there's something else I need to address real quickly here. So for the integral of tangent, well, that's going to be the integral of sine of x over cosine of x. Okay. So now the question: what's our choice for u? Cosine of x. Even though the derivative is negative sine. Here's why. If you make the other choice, which is not going to work out, what's my du? Cosine of x times. Do we have a cosine of x times dx? We do not. We have a 1 over cosine of x times dx, aka secant of x times dx, a totally different thing. So this is the wrong choice, which goes back to what I was saying before, is how you usually want to pick the u that is stuck somewhere. Even though either choice here seems like the du is the other thing, you want to make sure you're picking the right thing to be the u. So here we're going to pick u equal to cosine of x. Our du is going to be negative sine of x times dx. We're going to multiply both sides by -1 to say that negative du is equal to positive sine of x dx. And then we're going to rewrite our integral as the integral of negative du all divided by u. Or again, if you prefer, negative integral of 1 over u du. I don't think you need to write this, but it's not wrong to write it if you want to write it. We get negative natural log of the absolute value of u plus c, which then becomes the negative natural log of the absolute value of cosine of x plus c, which sometimes is alternatively written as the natural log of the absolute value of cosine of x to the negative first power, which is the natural log of 1 over the absolute value of cosine of x, which is the natural log of the absolute value of secant of x. Either one of these forms is completely acceptable and correct. And people write either one depending on how they feel. So unfortunately, right, there's no like agree like this is better. Sometimes we just write one or the other. There was something I just thought about. Oh yeah, I know what it was. So this pulls us back to the mini u-substitutions we were doing at the very beginning of the co class, where I was talking about how like you can just do the integral of like say cosine of 4x dx by saying, well, we know the integral should be something like sine of 4x, but we know it's not exactly sine of 4x because of the chain rule. If you took the derivative of this, you would end up multiplying by a constant factor of 4. So we need to divide by 4 to account for that. But really, that's just a u-substitution that we didn't show the work for. Now, do I think you should show the work for a u-sub like this? No, I don't. I think you should try to get comfortable with what we usually call mini u-substitutions, where your u is just a multiple of x. So if we were going to do the u-substitution here, here's how it would look. We would say that u is equal to 4x. My du is 4 times dx, or 1/4 times du is equal to dx. So the integral is going to become the integral of, well, my dx is 1/4 du, and my cosine of 4x is cosine of u. We integrate. The antiderivative cosine of u is sine of u. The multiple of 1/4 hangs out, plus c, and then we plug back in what u is equal to, and no surprises, we get 1/4 sine of 4x plus c. So that's why that was working the way it was way back when. But again, I don't think you should show the work for this in general, because people kind of have an expectation that, yeah, that's a small enough u-substitution that you can just do it without showing your work. Yeah. Yeah, 2 minutes is not enough time. Okay, let me do one more. There's one more thing I want to point out. Where'd you go? I'm trying to remember the example I'm thinking of. Oh yeah, I know what it is. All right, sure. So let's say we have the integral of, this one's kind of tricky, but I like it. Is that right? Yes. Okay. This one is harder to see what your choice for u should be. It is not the denominator. Here's why. You let u equal 1 plus e to the 2x. Your du is e to the 2x times 2 dx. And even if I get rid of the 2, I don't have an e to the 2x times dx. I have an e to the x times dx, which is very different. But the fact that I have an e to the x times dx tells me about what I might use as a choice. We have e to the x times dx, meaning it might be useful to choose a function whose derivative is equal to that. In other words, we might choose u equal to just e to the x, because our du is e to the x times dx. All right, here is an example of if you do the things in the wrong order, it's going to be terrible. I'm going to write this the following way. I'm going to write the integral of e to the x over 1 plus e to the x squared times dx. And here's how to do this the wrong way. Don't write this down. All my e to the x's become u. This is wrong. Oh no, I didn't deal with the dx turning into du. I can't do the integral. That's why you have to make sure that this part gets soaked up by the du, right? That e to the x up there doesn't turn into u. That e to the x is part of what du is equal to in the e to the x times dx. I will say this is one of these that people like doing it the other way, where they solve for dx and then divide by stuff because it feels more straightforward. I don't know. Anyway, doing it this way, we get the integral of du over 1 plus e to the, 1 plus u squared. Sorry, that's terrible. And then that's something we know how to anti-differentiate. That's going to be the arc tangent of u plus c, which is then the arc tangent of e to the x plus c. So, word of warning, when you're doing u-substitution, make sure you turn dx into whatever du thing needs to be before you do anything else. And that means you have to grab whatever pieces go with dx to turn into du, and then the rest of the pieces you turn into u's. All right. Have a lovely 5 days until I see you again. Have a nice picnic day. Everything in moderation. I'll see you on Tuesday.